All right, so this is lecture 2 of Math 676, and what I would like to do is just give you a very brief overview of this library that's called deal.II. That is the topic of this class. So deal.II is essentially a library that offers everything that you want to do with finite element methods. So in particular, what you need for finite element methods is you need to have a mesh. You need to have the finite elements, that would be, let's say, the shape functions. Then, of course, you need to have a mapping, for example. You need to have quadratures. You need to do all of the things that you need for your linear algebra. And then deal.II also offers you a huge collection of tools. Let's say you need all sorts of things that help you with this and that typically happens in a finite element code. And I will give you a very brief overview of the sort of things that deal.II offers in all of these regards. So if you want to download it, or if you want to look at it online, there's a web page that is called deal2.org, spelled dealii.org. So deal.II is a library that falls into a class of, there are other libraries too that implement finite element methods. It is arguably the largest ones of these. It's probably also the most widely used one. So just to give you an idea of how big it actually is, it has on the order of 600,000 lines of C++ code. That's maybe 30 years of work invested in this, not just by a single person, but by a whole collection of people who are working on this. It has on the order of 10,000 pages of documentation, maybe more, and it has today some 45 tutorial programs. And what I'm going to do in a good part of this semester is that I walk you through these tutorial programs, that I show you how to implement problem X, which is what, let's say, step 14 is about. So I'm going to show you these tutorial programs. They build from very simple programs to very complicated ones, and show you different parts of this library. deal.II is fairly widely distributed. It has on the order of 20,000 downloads per year. And we know of a good number of publications that build on it. So last year, for example, we know of at least 65 publications that cite the main paper that describes deal.II. But there are probably many more. So there's on the deal.II homepage, there is a link to a page that lists all of these publications. So in particular, if you want to solve a particular problem, it would be very much worthwhile to go to this page and take a look at what other people have done and see if there's something similar that you can already use. It's used in teaching, not just in Math 676 here at Texas A&M, but it is also used at various other universities around the world as a teaching tool for finite element methods. And finally, me and my co-authors got the Wilkinson Prize in 2007, which is a prize that is given for high-quality mathematical software. Okay, so just to go through the list of things that deal.II offers. As far as meshes are concerned, for example, when you want to do finite element meshes, they, of course, need to come in 1D, 2D, and 3D versions. So, of course, the real world is three-dimensional, but oftentimes we can get away with doing things in 2D. Particularly because it's so much cheaper to do it. So if you, one of the things you will realize that even in 2013, when we taped these classes here, that 3D computations are always expensive. And if you can do, let's say, the software development, or maybe even the solution of the real problem that you want to do in 2D, for example, by exploiting some rotational symmetry, maybe your problem really is two-dimensional, then you will find that it's a lot easier and a lot cheaper to do this, a lot faster too. Then what we want to do with these meshes is that we want to refine them adaptively. So what this means is we solve a partial differential equation and we find that the solution, for example, is very smooth in part of the domain. There's no real reason to have a fine mesh in that part of the domain. Whereas if the solution has spikes or is rough or is oscillatory in other parts of the domain, we need to have a fine mesh there. So adaptive mesh refinement refers to the fact that we want to look at the solution, refine the mesh, make it finer in parts of the domain, but not in others. And so we want to do this in 1D, 2D, and 3D. Of course, like so many other things, if you had to implement this by yourself, it would be very difficult. But deal.II comes with a couple of classes that implement, let's say, the most common ways of adaptive refining a mesh already built in. So it's fairly easy to do this, and I will show you this in the step 6 tutorial program, how to actually do this. You will find that it costs you about 20 or 30 lines of actual code to use adaptive mesh refinement. Then there is, of course, a wide variety of finite elements that people use for finite element computations. So there's the usual continuous and discontinuous elements, let's say the Lagrange interpolatory elements of various different orders. Let's say the Q1 element as the lowest order, but then you can have a Q4 or Q5 if you're interested in this. But then for particular problems, there's also, for example, the Nedelec element for electromagnetics. There's the Raviatoma element for the mixed Laplace, and so on and so forth. And all of these sort of things are already there in deal.II. And then one of the things that you get to appreciate a lot when you want to solve more complicated problems is that most real-world problems have multiple components. So, for example, let's say I'm going to show you a picture of a code that solves convection in the Earth's mantle, where you would have not just the velocity and the pressure, but the temperature and maybe the chemical composition and all sorts of other variables that you have to compute. And so this is a typical example of a multi-component problem. And there is a lot of support in deal.II for these sort of multi-component problems. And we're going to get back to how to use this sort of support in one of the tutorial programs. Then once you have a mesh and you have a finite element, the next step that you come out with is that you need to do linear algebra. So you have to solve a linear system, for example. And for this, deal.II has its own sublibrary for dense and sparse linear algebra. So it has classes that can store matrices and vectors, for example. And it has classes that implement linear solvers like the conjugate gradient method, CG, or GMRES, or any of these sort of things. But it turns out that for parallel computations in particular, that is a very expensive proposition to implement these sort of classes yourself. And for parallel computations, we built on two libraries that are called PETSI and Trilinos that do this vastly better than we could ever hope to do it ourselves. These are libraries that are developed by the US National Labs, PETSI at Argonne in Chicago, and Trilinos primarily in Sandia in Albuquerque, New Mexico, that implement a vast amount of linear algebra classes for parallel computations that have been scaled to hundreds of thousands of processors, so to the biggest machines that we have today. And then we also have interfaces to a package that's called UMFPACK. That's the Unstructured Multifrontal Linear Solver package. That is a direct solver, which is typically the first go-to solver for a linear system, for a sparse linear system on a single processor, if you just want to get it solved. It's a direct solver, so it typically needs a lot of memory, but it always works. And so I'm going to show you how to do this. Then deal.II, of course, has classes for pre- and post-processing. So it doesn't do mesh generation, but it can read meshes in a good number of standard formats. And in particular, it can output data in almost any visualization format you can think of. So again, we don't do the visualization ourselves, but we can use formats that high-quality visualization software can use. And again, I'm going to show you how to do this. Then deal.II supports parallelization. On a single machine, let's say my laptop here, we can use threads and tasks. If you have a cluster with many thousands or tens of thousands of processors, we do this via MPI. And we have done computations on tens of thousands of processors. So you can scale this to fairly large problem sizes. Now, let me give you just a very brief overview of the sort of things that people have done with deal.II. So when we started deal.II in 1998 or 1997, we really wanted a tool that would allow us to solve problems that we wanted to do in our mathematics research. But it turned out that ultimately we came up with a tool that has apparently a much wider usage. So people use it for practically every PDE you can think of. So I did this little survey of what people used it between 2008 and 2010 alone. So there's papers, for example, that use deal.II on biomedical imaging, on simulating heart muscle fibers. Then in fluid dynamics, microfluidics, oil reservoir simulations, fuel cell simulation, aerodynamics. People used it for physics studies in quantum mechanics and in neutron transport. Of course, they use it for numerical methods research, which is my own background and the background of the institute that we started this in. But then there are many more people in, let's say, solid mechanics that do fraction mechanics, damage models, sedimentation, biomechanics, root growth of plants, solidification of alloys, glacial mechanics, whatever you can think of. One of the more interesting studies that I found was that somebody simulated how statues in Rome decay due to air pollution. So you see the wide range of problems that people solve with this software. And what I hope you will see over the next few classes is how this works. How does deal.II give you the flexibility to solve all of these problems that may come from a vast variety of different fields. Just to give you one example of a nice picture that we created a while back, and of the sort of things that you can do. Me and a postdoc of mine, Timo Heiser, wrote a code that is called Aspect, and you can find that at the website aspect.deal2.org, that solves problems in convection in the Earth's mantle. So in the Earth's mantle is the region between the Earth's core that would be down here and the Earth's crust that we're standing on that sits at the outer edge of the Earth. And what people want to simulate is the convection of material, because what is happening is that the Earth's core is very hot. So at the bottom of the mantle, it's much hotter than at the top, and you get exactly the same sort of behavior of this material in between that you have, let's say, from a pot that you put on a stove, that you have hot material that rises up from below and cold material that falls down from the top. And so people want to simulate this because they want to understand, for example, what is it that drives continental plates? What is it that drives mid-ocean ridges? Why do we have earthquakes and these sort of things? So that's sort of the motivation for this code Aspect. And what we want to do with this is that we want to solve problems in 2D and 3D. You see, if you look at these plumes that rise up here, that the features that you have are fairly small compared to the overall size of the Earth's mantle. And that if you want to resolve them accurately without investing too much compute time, that you need to have adaptive meshes just like over here that are refined where it's necessary, and that you have coarse meshes where nothing's going on. Okay, so we need a code of this kind, and then we found that it's efficient if we use higher order finite elements because we can get a more accurate solution, and it turns out that to solve these sort of problems in 2D and 3D, we need to run this on hundreds or thousands of processors. So that is just one of the examples of codes that you can build on it. So you see that there's fairly complicated physics going on here that you need to resolve and describe, and deal.II is a tool that provides you basically all of the, let's say, building blocks of this sort of thing. So the actual Aspect code is not very large. The part of Aspect that deals with the, let's say, description of the physics is maybe 2,000 or 3,000 lines of code. But we can make it this small because it builds on a software that has on the order of 600,000 lines of code. So let me just briefly talk about how deal.II is developed. So there's, let's say, 4 to 6 core developers in the United States, in South Africa, in Germany, and then there's a whole number of people who occasionally contribute code, maybe on the order of 10 from around the world, essentially. These people come and go for these sort of projects. It's an open source project. Over the course of the last 10 years, we had contributions from more than 100 people. And with all of these people working on this joint project, the code grows at roughly 3,000 lines per month. And this is a a number, 3,000 lines of code per month, that has been steady for the last more than 10 years. deal.II is a typical open source project. So there's a small number of people who, let's say, run this project. But then there's a significant number of other people who essentially need functionality for whatever they do right now. And so if whatever you want to solve right now, if you need to implement something that is general enough that you think that other people could use it too, they often contribute it to deal.II, and then it becomes part of the software library. This is essentially how open source software works. Somebody has an itch, and they scratch it, and the code that is produced as part of this will become part of the project. So deal.II, as I say, is a fairly typical open source project. What all open source projects rely upon is essentially volunteer work. And one of the things that I would really like to encourage you is, if you use deal.II and you implement stuff, please contact us about it. What you do likely has impact for somebody else too. It never happens that you implement code that nobody else can use. And so what we really try very hard is to be a friendly community of people who are, willing to give credit where credit is due for contributions that other people bring to the table. And so we really try to be a community, not just of the main developers here and in Europe and in South Africa, but that there is a collection of people who all work together on this one project. So if you have something that you think is worthwhile contributing, please consider that. There's mailing lists where you can send emails to, you can ask us directly. And we're quite happy to work with you on these sort of things. Maybe to give you an idea of the, let's say, professional kind, and let's say the style of software development we do. So it is quite professionally managed. The people who run this project, let's say the core of it, have worked on this for many years. So, for example, we have a source code repository that is accessible to everybody openly. We have 2 mailing lists for user questions and for developer discussions with many emails per day. But then we try to build this really as a professional, not as a commercial project, but as a professional grade software project. So for example, we have many tests that we run after every change to make sure that everything we do maintains current functionality and that we don't accidentally break something that worked before. So right now it's on the order of 2,700 tests that we run after every change. But then there's also relatively professional installation instructions and tools. For example, we can build on Linux, we can build on Mac, we can build on Windows. There's a variety of websites that track all sorts of information about this project and that help us develop this software. What I'm going to talk about during this course is how to use deal.II on Linux. So my laptop here runs Linux, and I will show you all of the steps that you need to do if you want to install and run programs based on deal.II, how to use visualization and development tools and so on and so forth in Linux. There is not that much difference if you want to do this on Macintosh, for example. Macintosh essentially is under the hood a Unix-like operating system as well. And so if you know a little bit about how to work on the command line under Unix, then that works exactly the same way under Macintosh as well. Under Windows, it is a little bit different. Windows has an environment that is called Cygwin that, let's say, provides a Unix-like environment to Windows, and you can run deal.II on this as well. We're working on native support for Windows as well. That's a little bit more complicated. We hope we get there sometime in the near future. So if you want more information about deal.II, the website for this is called deal.II.org. And I will show you aspects of this website many times throughout this course. Let me just show you how to navigate this website to begin with. So if you type deal.II.org, you come out at this particular page here, where you have the front page describing what deal.II is. Then there is installation, download instructions over here to the left, then installation instructions in the README. There is the documentation for various different versions of deal.II. So right now we're up to 7.2. I hope that by the end of the semester we're at 8. There is subversion here is the documentation for the current development version. There is frequently asked questions. There's a page with news, what's going on in this project. There are mailing lists, there's a wiki, there's bug trackers, and so on and so forth. So during this semester we will walk through a good number of these individual links here and see where that leads. So just to conclude this section, the mission of deal.II is to provide everything that is needed in finite element computations. And of course, we will never be able to provide everything, but to provide, let's say, most of the things that many finite element codes use. And you will find that almost all of the things that you will need for your code that are not specific to that particular problem, but as, let's say, that have to do with the finite element description, that is there in deal.II. And then the development methodology is that it's an open source project, so there is a community that invites you to participate if you want to, but also a community that provides you with resources. Let's say if you have questions, these sort of things, the community is very forthcoming in helping you with. And I hope that I showed you through, for example, the example of the tests, that the software is professionally developed, so it is certainly something that we know is relatively free of bugs. I think with this, we conclude lecture 2, and we'll come back in the future.